Okay, we're back to finish up ramps. Let's do a slightly more difficult problem this time. We're going to add some more things in here. A box on a steep ramp is attached to a rope that will pull it up the ramp as shown below. There is some friction between the box and the ramp. So already, before we even get to the free body diagram, we're adding in at least two more forces. Obviously, there's a force of tension now pulling the box up, and there's some friction between the box and the ramp. Last time was about as easy as we could get with a ramp question, with just a normal force and force of gravity. Now we're getting into a slightly harder question. Draw a free body diagram for the box, write the net force equations. So that's going to begin about the same way as last time. We're going to have a box. This time for my axis, I'm going to draw it, since the box is getting pulled up the ramp, I might as well make the direction it's getting pulled the positive x direction. I'm going to tilt my axis again, and I'm going to go through, as I'm talking through this, I'm going to go through most of the, I'm going to go through the same sort of stuff that we did last time, but just in a little bit less detail. If you forget why I'm doing something, just go back to that last video and take a look. Okay, so the force is on the box. Obviously we have tension going up the ramp, like so. We have a normal force perpendicular to the ramp surface, okay, in that direction. We have a force of friction. If there was no friction here, we know that the box is going to get pulled up the ramp anyways. That means friction must point down the ramp, like that. And then we have gravity, which just points straight down, not in the direction, in the negative y direction, because that's tilted here, but just straight down. So we have tension in the positive x direction, force of normal force in the positive y direction, force of friction in the negative x direction. Force of gravity is in neither of those directions. We can see it has components in the negative x direction and the negative y direction. So this needs to get split into components, like so. Now, this second component that I'm drawing right now might freak some people out. They might say, wait a sec, you already have a force in that direction. So what? You can have as many forces in any direction as you want, okay? There's no limit, there's no rule that says you can only have one force per direction. Some people also like to say that, oh, that component must be equal to the force of friction, therefore. No, they're completely different things. This is the force of gravity, this is a component of the force of gravity, and this is the force of friction. They're completely separate forces. All right, so we need to figure out where theta goes, number one, and then figure out what the names of these components are. So just kind of sketching what I had last time. I know that this is a right angle right here, so 90 plus theta. This must be 90 minus theta. And since I have a perpendicular line right here, that would mean this is theta, which means by looking at it, this is the angle that's 90 minus theta. This must be theta. This component is adjacent to theta. It's right next to it. So this must be the component that is Fg cosine theta. This up here must be the component that is Fg sine theta. Now, my net force, or my free body diagram is done. Once I've got everything split up into components that needs to get split up into components, now I write my net force equations. We'll start in the y direction. This is the same as last time. Fn minus Fg cosine of theta equals MAY. This box is not going to suddenly blast off this way or sink down into the ramp this way. Therefore, it's not accelerating in the y direction. It's not moving in those directions, and it's not about to start moving in those directions. So that must be 0. Therefore, I get that the normal force is equal to mg cosine theta. The x direction is more complicated this time. I not only have just one force as last time, now I have 3 forces or components in that direction. In the positive x direction, I have tension. In the negative x direction, I have the force of friction and a component of the force of gravity. Since those are both in the negative x direction, they both get minus signs in front of them, and that's equal to MAX. Now, I could stop here, but I am of the opinion that it's always good to try and write things in as simple of terms as possible. Now, simplest terms doesn't mean the least amount of terms, it means the things that are easiest to measure. Or if you have equations for things, it is a good idea to substitute in. So I'm going to look at this FF. Since this box is moving, it's moving up the ramp, I know that this is kinetic friction. So I know that I could write this as mu times Fn. Fg, as we know, is just mg sine theta, so this can get turned into mg sine theta equals MAX. I can go even a step further because I just solved for what Fn is and plug that in here. So my I could get down to this level. Mu, Fn, is really mg cosine theta minus mg sine theta equals max. And I could actually go one step further. You'll notice that both of these terms have an mg in them. I'm going to take that mg out to the front. So I could write this, and you don't have to do this, but this is my tendency. I could write this as t minus mg, in parentheses, mu cosine of theta. Okay, if I multiply that back in, I get minus mu mg cosine theta. And here, I should, if I took the negative mg out, I'm left with just sine theta. And parentheses equals max. You don't have to do that, but that's my preference, is to pull things out as much as possible. Okay, and you'll see, I mean, I could leave it like this, but that means that there's going to be a lot more work to do down below. If I do this, now I have everything written in terms that are fairly standard. Tension minus mass times acceleration due to gravity. That's a constant. Mass is pretty easy to measure. Mu is usually given to you if you know the two surfaces. The theta, the angle, is given to you, equals max. Okay? If I left it like this and I wanted to know, let's say, the acceleration, I would have to go through a whole bunch of calculations probably to figure out what ff is in the first place, or figure out what fg is. Here I've got it written as simply as possible, as in its most expanded form. Let's move on to the questions. If the coefficient of friction is 0.22, the angle is 50 degrees, and the force of gravity on the box is 200 newtons, what is the necessary tension in the rope to pull the box up the ramp at a constant velocity? Well, let's take our equation here. Let's just rewrite it to start. T minus mg, parentheses, mu cosine theta plus sine theta equals max. Now, you might say, okay, so we're looking for t. We don't know the mass. We do know acceleration due to gravity. We do know the coefficient. We do know the angle. We know the angle. Don't know the mass. But it says, we might look like we don't know the acceleration, but we do, because we're told it's at a constant velocity. So what I'm going to do here, constant velocity means no acceleration. I'm going to cross this off, and I'm going to move that entire term to the other side. So I have t equals mg, parentheses, mu cosine theta plus sine theta. And, interestingly enough, I'm told the force of gravity is 200 newtons. I know one of the equations for the force of gravity is Fg equals mg. Since the force of gravity is 200 newtons, that means that mg must be 200 newtons. So I know that this term right here is 200 newtons. I can just plug in. T equals 200 newtons. And again, the only way I can plug in directly for this is because I wrote this over here on this side. If I had just said that, oh, this must be 200, I would say, well, no, you have to prove that to me. How do you know that that thing that you're telling me is actually 200? Coefficient of friction is 0.22 times the cosine of 50 degrees plus the sine of 50 degrees. Okay, so make sure you do this in the right order. We have to multiply these two first, then add sine of 50, then multiply by 200. 0.22. Oh, I'm going to start with the cosine. 50 cosine times 0.22 plus 50 sine equals times 200. I get a tension of a little bit under 182 newtons. So I'm at 181.4, or actually, let's round it, 181.5 newtons. Let's talk about why that is useful. Why do we use ramps in the first place? We use ramps to reduce the amount of force required to get something from a low point up to a high point. Okay, ramps reduce the amount of force required. Humans are not good at exerting very big forces. We can exert smaller forces for a long period of time. That's what we're built for. This box has a force of gravity on it of 200 newtons. If we had just wanted to lift the box ourselves, it would take 200 newtons in order to do this, to just lift it up with our hands straight up. Okay, we would have to overcome the force of gravity. With this ramp system, we see that the tension required to get the box to move up the ramp is 181.5 newtons, which is less than 200, about 10% less. Is that useful? Maybe, maybe not. Okay. If we had reduced the coefficient of friction more, would this be Would this be the tension be even less? Absolutely. If we reduce the coefficient of friction even more, we would have a situation where the tension is much less, because if we reduce this, that's going to reduce this whole thing, which is, when we multiply it by mg, would cause the tension to be less. But that's not the case that we have, okay? So this is somewhat useful. What wouldn't be useful is if we had a very high coefficient of friction, and therefore pulling the box up the ramp this way was actually more than 200 newtons. That would be a non-useful use of this ramp, or use of this technology. Now, last question. What is the necessary tension in the rope to pull the box up the ramp at a constant acceleration of 1.5 meters per second squared? Again, let's go back to our equation. T minus mg mu cosine theta plus sine theta equals max. Now this time, we do actually have to figure out what the mass is. The reason we have to figure out what the mass is because we need to just plug in the regular mass right here along with the acceleration. But that's easy enough to do because I already know the force of gravity is 200. G we approximate as 10 meters per second squared in this class, so the mass must be 20 kilograms. If you were converting that to pounds, it's about 45 pounds or so. So now I'm going to plug everything in again, and again I'm solving for the tension, okay? T minus 200 newtons, 0.22 times the cosine of 50 degrees, plus the sine of 50 degrees, equals 20 kilograms multiplied by 1.5 meters per second squared. Well, if you look at it, this term is going to be the exact same, okay? The force of friction didn't change, the component of the force of gravity didn't change. All that changed was this max term. In other words, we now have a net force where we did not before. So this whole thing is going to be tension minus 181.5 equals 20 times 1.5 is 30. So the tension minus 181.5 newtons equals 30 newtons. The new tension, in order to cause the box to move up the ramp with an acceleration, is 211.5 newtons. So in order to cause it to move up quicker, we see that you have to pull harder. There has to be a greater tension. Now, again, we now have a net force, mass times acceleration, of 30 newtons. Where did that net force come from? What force changed? It must have been the force of tension, because look, the tension is exactly 30 newtons bigger. The force of friction didn't change, and the component of the force of gravity didn't change. Okay? So that's a little example of how we can use, how we can solve questions involving ramps. There's many, many other types. You guys will see many questions involving ramps. We'll do some experiments with them in class. The next topic that we're going to get to is the one of my personal favorites to teach in AP Physics 1, actually, and that would be free body diagrams involving two or more objects. I'll see you later.